Hello everyone, good morning. Thank you for waking up early. Thank you for coming. It's an absolute pleasure to be here in Oslo. If you can't tell from the accent, I've come all the way from Australia. Hopefully I don't have too many colloquialisms that you won't understand, but I think we should be right. My name's Dave, says somewhere. I work for Microsoft. I work on part of .NET, part on the .NET tooling side of things, so the project system team, which is part of Visual Studio. And I'm not talking about any of that today. This is all just my own experience, and the first half anyway is largely my own opinion. Things that I think are good to think about. So, premature optimization is the root of all evil. I won't bother asking who's heard this saying, because I'm pretty sure everyone has. It's fairly well known and popular. Does anyone know who said it? Anyone want to shout a guess? Very good. Donald Knuth or Knuth or Nuth, or I'm sure he knows how to pronounce it, but I don't. So this is a short little 8 words. Yeah, 8 words. And it gets doled out reasonably often in certain, I won't say disparaging, but I've seen quite a few times, someone will post, let's say, a simple message on Twitter, like, here's a code snippet, should this use a list or should I use an immutable list? And invariably there's always someone who will reply, premature optimization is the root of all evil. Possibly thinking they're helping, possibly not, we don't know, it is Twitter. And it's usually said as I think, as a means of laziness it's sort of an excuse to be lazy. So there's actually, I was actually on a pull request that I submitted. This was in my previous job, not Microsoft. And I wrote a for each loop, or it was probably like some nested for it. It was a reasonably complex code that iterated over something, but I did it as a for each loop. And I got a comment saying you could rewrite this in one line using link. And I replied saying, yes, you could, that's right, but it would be a little bit slower and it would use more memory or whatever it was. And I personally find this to be just as readable. And the reply from that person was then, you shouldn't have done this because link might be slow, because that's premature optimization. And they doled out this message. What I should have done was write the link query, because that's the single line. Some people like, one line of code where possible. And then if performance is a problem, then you solve it. And I kind of get that ideal. You don't want to be going down a rabbit hole unnecessarily. But I also think that, firstly, that's kind of making your users find your performance bugs, which is not very good. I think we can all agree. Or maybe you're lucky and you have a QA department who'll find them for you, but either way. But I also think that's not really the spirit of what Donald Knuth was maybe trying to say. Because it turns out Donald Knuth actually said more than just 8 words. As you may be able to tell by my weird placement of text in PowerPoint, I do actually know how to use PowerPoint. This is part of a longer sentence. And if we add a little bit more context to this, I think things get a bit more interesting. So the rest of this sentence is, we should forget about small efficiencies about 97% of the time, ... yet we should not pass up our opportunities in that critical 3%. And I think that's really kind of telling, because when you take these 8 words out of context, it kind of sounds like never think about performance, it's always a bad idea. And what Donald Knuth is actually saying is sometimes it's super critical to think about it. And what's sort of unwritten here is, to me anyway, you have to think about whether your code is in that 3% before you then know whether you can think about performance, right? So, don't shy away from it. Now, I promise I do know what I'm doing with PowerPoint. There's even more that we can bring into this, and obviously this is, you could keep going forever, but the sentence before this, I think, sort of completes the picture. So it says, programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their programs, and these attempts at efficiency actually have a strong negative impact when debugging and maintenance are concerned. It's a very long sentence. To me, this sort of like completes a picture, because when I think about how we should treat performance, you should never say, don't do it, it's the root of all evil. But you also shouldn't say, focus on that above all else. So Knuth mentions debugging and maintenance. You know, I would add in there things like readability, and I guess maybe scalability in today's sort of more different world. Like, so this passage here comes from like 40 years ago, so obviously computing was different then. But to me, what this means is, don't focus on any one thing, you have to think about all the things. Now, for bonus internet points, does anyone know what article or book or essay, I don't know, this came from? I didn't think so. I didn't either. Don't worry. But I think it's kind of funny because, so the people on Twitter who spout out premature optimization as the root of all evil as a way to make themselves seem smarter, they probably also don't like it when people use go-to statements. And this little passage came from structured programming with go-to statements, where it's kind of funny. And actually, it's kind of fitting because this is an argument for where go-to statements make sense. And, you know, there's times in programming where everything makes sense. It's all a matter of how you use it. So anyway, on to what, if I read in a little bit and take a bit of poetic license, what I think Donald Knuth was talking about, and what I think anyway. Essentially, coding is about trade-offs, right? As programmers, it's our job to decide, is performance important here, or is readability more important, or maintenance, or all the rest of them. And if we didn't do that, if we didn't have that as part of our jobs, we're essentially just typing, and that's kind of boring. And so performance is absolutely one of the factors, and it should be considered all the time, but it's only one of the factors, right? The job is about balance. So we need to work out, how do we weigh up these factors? How do we weigh up the maintainability and debuggability and readability and the performability of stuff, right? Thinking about optimization is good. You have to think about it in order to decide whether acting on it would be premature, right? So it's got to be part of your thinking. And ideally, if you can, at work, in your teams, if you can bring in performance thinking as part of the culture of work, then you get better results. You know, if this pull request where someone writes a link statement and you might be worried that maybe it's going to be too slow, well, if you trust and if you have a culture of this sort of thinking in your teams, then you can trust that the person who wrote this has thought about it and has worked out which is the more appropriate thing to go in favor of, readability versus performance. And this is what they've come to. Now, hopefully there might be a comment at the top saying, I'm doing this because, but, you know, getting to that level is a good thing, and it kind of elevates a whole team, right? When junior programmers see senior programmers making these trade-offs and where the trade-offs are visible, then it educates them about that aspect of the job. So how do you work out what's important, or how do you work out when performance is important? So you have to know a bit about what you're writing, which makes sense. You have to know the context of your execution, right? If you're writing code in a web service that's going to get hit 100 times a minute, then that has some performance needs. And if you're writing code in a web service that gets hit only from the back-end, admin site, and it's from a button that gets pressed once a month by the accounts person at the end of the month when they're reconciling books, you maybe can make some different trade-offs, right? But you have to know where your code's going to execute and how often. And then you have to know what kind of data your code is processing, if it's processing data. So where I used to work, we worked with universities. And some of the universities were very smart and would make a web service call to our system when a student's data was updated with a change that we cared about. So we would only get the messages that we needed, which was great. And then some of the universities, their IT systems were a bit older, and all they could do was give us a batch file that had, all of the student data for all of the university campus. We might have cared about 10% of it, and then we had to go and work out what has changed. So those two systems, they're both ostensibly importing data, but they have very different requirements. You have to validate your assumptions. So this web service call that was coming in, can you assume that it only comes in when you need to know about it? Or is there maybe some difference in business logic there between their system and ours where maybe they don't know when we need to know about it? Can you assume that this file is always going to have this many records in it? Validate your assumptions actually goes down to even like the lowest level. I've seen people where they'll write some code and someone might say, well, this is inefficient or whatever. And they'll say, oh yeah, but the compiler will optimize that, or the jitter will fix that for me. And that's cool, sometimes it does, but you should check, right? And then you have to consider the worst case. One of these big imports that ran on, was like 100,000 records in this file. So the university kicked off our import at 1 a.m. so that no one was using the system, and less chance of database locks taking longer, whatever. And it ran in about 7 hours, which was okay. But what happens over time if that starts getting longer? What happens if your nightly run takes 10 hours and now starts to overlap with the working day? Or what happens in the worst case, what happens if your nightly run takes 26 hours and you're now past when you should have done the next one? Do you do another one, or does that cause overlap? Or do you skip a day, or does that cause problems? And you've got to think about all these things. And then make sure you think about the bigger picture of what you're doing as well as the actual code you're implementing. So, if you're importing a list of 100,000 students, don't worry about optimizing a method that takes an array with 100,000 things. Think about whether you should have an array with 100,000 things in it. Think about the big picture. But if you can get down to the level where you can say, this code path is where I have a performance problem, then micro-benchmarking that is a super effective way of really nailing down what is a good approach and what's a bad approach. And that's kind of what we're going to be talking about today. But you have to sort of think about all these things before you can get to that level. You're not allowed to benchmark your whole application and say, well, this run took an hour, and now I'll try this one, and this takes an hour and 3 minutes. Not allowed. So, how do we do performance work? Well, this is a very simple slide. The only way to assess the performance of code is to measure it. Obviously, you can bring your experience to bear, but hopefully that experience is brought out of a series of times where you have measured things. You measure your code, make some changes, and measure it again. And maybe you try 5 different things, measure them all. You can't look at a piece of code in complete, void and determine which one's going to perform better or worse, because there's so many things. Hopefully I'll illustrate that. Anyway, this brings us on to this line of code. This line of code is what caused this talk to be created, because I saw this code in a pull request. Someone wrote this. And I stared at it. And I stared at it for about 5 minutes, because I actually don't really use I haven't really used the aggregate method much, and I didn't know what it did. And in case you don't either, so aggregate is one of the extension methods that came in with link. Data in this case was a list of strings. And what this does is it turns a list of strings into a comma-separated string. And I looked at this and I went, well, that seems like a really roundabout way to do that, because it's string.join, which is easier. And it's using link, and it's using a lambda and all these sort of things. And I said, well, don't do that, that's slow, and it uses too much memory. And of course, that comment is a really bad comment, and you should never leave that comment on a pull request. So I saw the error of my ways, right? That's slow. Well, how slow is it? And how slow is too slow? How fast does this code need to be? Right? You can't look at that method and tell me that's too slow, because you don't know what the rest of it is, right? Uses too much memory. Again, how much memory? Is this running on a Raspberry Pi in an IoT device, or is this running on a huge chunky web server? So, fine, I went away and I benchmarked. So, how do we measure how fast code is? This is the, hopefully you can see it, it's big enough. This is the sort of maybe first, maybe second attempt that people have to measure code. And there's a few problems with it. The first attempt that people usually do, I guess, would be without the loop. Right? The loop's kind of like, oh, hang on. Does anyone want to shout out some reasons why this is bad? If you're brave. You won't get hurt, I promise. Yeah.
No warm-up, please.
No warm-up, very good. Anyone else? There's like one sort of main thing that people notice, and that's it's using date time. So that can be bad. So this is the good version, right? This is the more complete version. And we'll just talk through what it's doing. So the first thing it does is sets the process priority and thread priority to as high as possible. And the reason for that is what we want to do when we're benchmarking, we want to measure our little payload. And we don't want anything else on the machine to affect that, because that's going to affect our results. So this is just saying, hey, computer, don't worry about the 300 tabs I have open in Chrome. Don't worry about my virus scanner. Try and give this process and this work as much CPU as you can, because the actual numbers here when we're benchmarking don't really matter. It kind of doesn't matter if this code runs in 2 seconds or 4 seconds. It's how this code runs compared to the new code you're going to write. Then we call our function. So that's our warm-up, right? .NET is compiled to immediate language. Immediate language is then run through the JIT, the just-in-time compiler, and that has to chew on your code for a bit. So letting the JIT have a go before we start timing means we're not measuring that time. So we warm up. And then we use a stopwatch. So stopwatch and date time are both as precise as each other. They both go down to the tick level, but date time, it's not granular. The values don't change as much. Wait, have I got that wrong? Is it anyway? One of them said, if you had a tight loop and you were outputting stopwatch ticks and date time ticks, they both output values, but you would see the stopwatch value change while the date time doesn't, and then the date time will kind of catch up after a while. So always use stopwatch. And it's not like it has any overhead. It's not actually timing. It just polls a high performance counter. So then we tell the garbage collector to go and do some stuff. And again, this is because we want our payload to be the only thing that matters. Garbage collection takes time. And if your payload needs garbage collection, then that's cool. You have to count that because that's a real world thing. But you don't want your measurement affected by collecting something else that happened before you got to your code. And then we have our loop, and then we output. The other possible thing that people in the past have commented that might be wrong about this is that it's looping 100 times, and maybe that's not enough. And that's a good point. It's kind of a little bit unknown. You can't, there's no like one answer for how many times to run code, but the theory is the more you run it, the smoother, you sort of smooth out the peaks, the quirks. The thing is, you shouldn't use this code either. Sorry for everyone who took a photo. The real way to measure code in .NET is to use benchmark.net. And this is, again, why this talk exists, because when I saw that line in the pull request and I said, no, that's slow, I thought, well, I've been meaning to try out benchmark.net, so let's see how it works. So benchmark.net, if you haven't heard of it, it's an open source project. It's part of the .NET Foundation, but that's, it's not official Microsoft code. One of the guys who works on it does work for Microsoft. One of the other guys works for JetBrains, so it's kind of even. But it's used internally by Microsoft by heaps of people, and it's sort of the main performance tool that the .NET Core use these days. So the Adam Sitnik is his name, he worked on benchmark.net, then got hired by Microsoft, and then has sort of helped to bring it in and move all the performance work that .NET Core has to it, and at the same time that's improved benchmark.net a bunch, which is good. It's super powerful, so you can use it to compare all sorts of things. I'm focusing on comparing my code because essentially that's where most of the problem's going to lie. I need to get my stuff right first, but you can use it to compare full framework versus .NET Core, or the legacy jitter versus the new Ryu jitter, or x64 versus x86, or all sorts of things. And there's, of course, plugins. People can write their own extensions, etc. And you can measure a bunch of things. You can measure speed and memory, and it tells you about garbage collections. It's got exports, got all sorts of cool stuff. How it works is kind of simple, but also kind of long-winded. So I'm not going to tell you. I'm going to show you instead. But this is not a demo-heavy session because benchmarks are slow. And that's a good thing, right? Most things when they're slow, especially since we're talking about performance, you think, oh, that's bad. But actually, it's good. And it's good because it's really thorough, which we'll see in a second. So, it's going to get bright. Should be big enough, hopefully. Right, let's write a benchmark. So this is a console application. All I've done is added a reference to benchmark.net from NuGet, and then I've built and saved and whatever, just so we don't have any Wi-Fi issues. There's no other cheating. There's no magical files here. It's just one program file. Because benchmarks are really simple to get started. So the first thing we'll do is we'll tell our benchmark runner to run our benchmarks, and I'm going to say to run all the benchmarks in the program class. And this is fairly standard for basic benchmarking, but as you build up suites of these things, obviously you have different classes for things. There's also a benchmark switcher, which can give you a little console app, like a little menu, which is cool. So we've told benchmark.net to run our benchmarks in this class. Simple as that. Now to write a benchmark, we just write a method. So string, we're going to use string join, and return string.join. I want comma separated, and I want to join my data. So I'm just going to recreate that little line of code. So for the data, I want it's got a string array, and I'll be lazy. You can kind of ignore this because this is not part of the benchmark. But there we go. So we have an array of numbers from 1 to 10. Obviously, this would be real data in the real world. Why is that green? Read only. Yeah, never mind. And so I've written a method, and this method is my payload, right? This is what I'm going to benchmark. I'm going to benchmark this string.join method, or string join method. Now, one thing you might have noticed is I'm returning a value from it. This is best practice for benchmarks because in the real world code that you're emulating here, you're going to use this value, right? The result of this string join. There are cases, and this one isn't one of them because the C# compiler is not quite smart enough to do this, but there are cases where if you don't use the value in your benchmark, if I just called string.join like this, it's possible that a smart enough compiler or jitter or something in future would know that string.join has no side effects and simply remove that line of code. And of course, if I do that, my benchmark's going to look really good, but I'm not going to be able to trust it. So we kind of pin our work by returning a value. And then the way we tell benchmark.net that this is something we want to measure is we just use the benchmark attribute. So this is now a benchmark.net program. I can run this will work. Obviously, benchmarking one thing is kind of irrelevant, right? What we want to do is compare. So we'll put in the other method, which is aggregate, and we'll compare the two. So it was start with string.empty, then it passes in the current state and the next state, and we return the next state. Is that right? Yeah, it compiles. All right. So I'm going to leave it like this. This is a simple, very simple benchmark, but I've got slides for slightly better ones with the same thing in a minute. All right, so then we run. Oh, one more thing before you run any benchmark. you have to be in release mode. If you're not in release mode, then again, you're not really getting a good benchmark, and actually benchmark.net will just refuse to run. So let's run the benchmark, and we'll talk through what it does once my machine compiles this horrendously long program. Here we go. Okay, so this is going to spin up some words on the screen, which you don't need to follow, but, oh, we've lost the left. There we are. So what benchmark.net does is it goes through a bunch of phases. And the phase that it's working on is this name in the left here. So we're up to workload actual. So it has, I think it's 5 stages. All that stuff about priming the jitter and things is mainly what it's trying to do. So the first thing it does is it actually works out, it measures itself to work out the overhead of having benchmark.net in your code. Then it measures your code plus itself to work out roughly how long that piece of work will take. And it does that to try to work out how many times to run that code. So when I said that 100 might not be enough, this is actually running my code 2 million times, right? So 2 million operations, that's for that one run. And you can see this is workload actual, so this is the real work. This is where we're really measuring. And all it's doing now is it's just doing this over and over again for some amount of time until this number at the end here, which is how long it takes, kind of settles down and stops being too peaky. And this is really important. So before, in my previous good example, I was running the code once to warm up the jitter. And that's cool, and it used to be cool in the past, but now we have a thing called tiered compilation. And what that will do is the more you run your code, the more aggressively the jitter will try and optimize it. So at the moment, maybe it takes 10 runs before it has finished trying its hardest and it'll leave you alone. But in future, that might change, right? So benchmark.net tries to just look at the numbers and just wait until things have settled down. You can see this is the start of a new run. You can see how choppy these numbers are, right? There's a 900, 800, we're over a microsecond. You can also see here now we're only doing 500,000 runs. So I can actually tell you right now, this is the slow one, right? You can look at this and go, well, one of these is clearly way slower than the other because essentially it worked out it couldn't do as many operations. And it kind of does that just so that, if your benchmark takes half an hour to run, it doesn't want to run your code 1 million times because that'll just take too long. Anyway, so it's finished. Now that only took 2 minutes. Oops, you can see here, runtime 2 minutes, 17 seconds. So that's not bad, but that's a really simple benchmark. As I've got some pre-canned results, and I'm running sort of 5 different things to benchmark, and it runs them 24 times each, so it gets long. The main thing we sort of look at here, though, is this table. And so you can see that string.join took, on average, 336 nanoseconds, and aggregate took 897 nanoseconds. So it's almost, but not quite, 3 times slower. And that's our answer, right? If all we were doing was trying to assess, is this method faster than this, there's our answer. And it is, it's not debatable, right? This is a number born of experimentation. There's no opinion here. There's no, but I like link and I like lambda expressions. That's cool. If you're trying to work out which is faster, this will tell you the answer. So it's actually a really good tool to solve arguments if you can get, you have to go through the argument that everyone agrees that this is a good thing to test. But if you can get to that. So some other things that it does. I'll just scroll up. Hopefully I can find, yeah, here we are. So is this on the screen? Almost. You can see here it says build script. So what this actually does, what benchmark.net does, and if you can see, it's kind of flowed over the end here, but it's a batch file. And then here there's an exe. You can't see the E and the X. What benchmark.net does is it actually recompiles your code. So it spits out a bunch of code to do the benchmarking, then it puts your code in the middle of that, and it compiles a new exe. So all that stuff I said about process affinity and like garbage collection and making sure no runs affect other runs, benchmark.net solves this problem by just every time it does something, it just generates a brand new exe. So when one benchmark finishes, it can't affect the other one because the whole process just goes away, which is really cool. So you can see, whoops, I can't scroll with the mouse. So you can see where it's working out the overhead of jitting. This pilot phase here, so it starts with 16 operations and then just grows exponentially until it gets to a number where it's big enough but doesn't take too long. I don't know the exact numbers it tries to aim for, but that's what it does. Then it does a warm-up, which is warming up the jitter and those sort of things, including all the code. But that's called the overhead warm-up. So that's measuring the overhead of measuring your code. So when I said slow, I meant thorough. You can see why. Then there's the overhead of actually running your code, and then we have all of the runs. So this one did 100 runs. This next one, it did 100 as well. Sometimes it stops after 30. It's really dependent on the numbers you get. I'm running on a laptop on battery power, and that has a reasonable effect on things. But that's our benchmark. Let's go back to our slides. So this is how easy it can be to write a simple benchmark. We can get a little bit fancier. So this is the real sort of benchmark that I wrote to actually answer this question of joining strings together. And so there's a few more things to this class. Firstly, there's two attributes at the top. One is memory diagnoser. So in that benchmark I just ran, all I was doing was measuring time. I wasn't measuring memory. Add in the memory diagnoser attribute, now we now we measure memory. The rplot exporter produces some nice graphs. You'll see them in a minute. There's also exporters that can produce flame graphs. You can get it to output the resulting assembler code of your methods. So you can actually, if you want to get down to it, see which one is more efficient in assembler. I don't personally understand assembler, but... And so then the next thing I'm doing here is there's this params attribute. So if you've ever used XUnit theories, it's a very similar concept. What benchmark.net will do with this code is it will run all of the benchmarks in your file, in your class, with that property set to 1. Then it'll run all the benchmarks in your class with that property set to 2, and so on and so forth. So this class has 5 benchmarks. There's 12 values in that array, right? This is going to run lots and lots of times. Each one, separate process, can't conflict with the other, so it's really thorough. Then we have our global setup. So this is like class initialize if we continue with the test metaphor. And they kind of end up looking like tests, and you kind of get into the same sort of mindset. So all we're doing here is initializing the data. It's kind of important that we do this in the setup method because benchmark.net will run this setup method once per iteration, but not once per operation, right? So the iteration was the 1 to 100 thing it did, and then the operation was when it ran the code 2 million times. And you need to be able to compare apples to apples. So if you're constantly randomizing your data, you're maybe not getting good results. So it's important to tell benchmark.net, hey, here's where I want to do my setup. And then here's the 5 things that I benchmarked. So first one on the top left, string concatenation. This is like the bad thing to do, right? This is what we're told never do, never use the plus equals operator on a string in a loop. Bad idea. Well, let's see how bad it is. Underneath that, we have string builder. That's the good version. This is what we're all told to do instead, so let's see. And then I thought, just for fun, up on the top right, I thought, what happens if I use a string builder, but I can work out how long this resulting string is going to be. So what happens if I tell .NET? Does it get any better? Then we have string.join, which is my favorite. And then we have aggregate. The only other thing that's different on this screen is there's this baseline equals true parameter here. And what that does is it simply tells benchmark.net for all of the times of running, compare them all against that method, right? And usually you would use this to say, this is my existing code, and here's 4 different attempts of how I could change it. And what this will mean is in the output table, they'll have a scaled column, and that method will always be set to 1, and then the rest will be set to something either higher or greater than 1. And if you really want to just make it super simple, do this with all your benchmarks, put in baseline, look at the table at the end, find the one that's underneath 1, that one's better. And if there's one that's above 1, it's worse, don't use that code. It's really simple. If you don't want to, if what you're trying to do is not get down into deep analysis, that just tells you the answer. So let's look at the results. This is kind of a hard graph to read, so there's some lines here. But we have aggregate So string link, aggregate method, string builder, an initialized string builder, string concatenation in a loop, and then string.join. So for one string, string concatenation wins. There's a tiny little blip here and a tiny blip here. And that makes sense because for one string, we're not concatenating anything, right? Our loop isn't going to do anything. For 2 and 3 and 4, string builder with capacity wins, with an initialized capacity. There's a really tiny little line there. You basically can't see it, but it's like a pixel high. And essentially, sorry, did I get that wrong? Yeah, sorry. String builder without capacity wins up to 4. Sorry. At 4, that's when string builder says, oh, hang on, I'm going to run out of room. And it has to go and do some work to allocate some more. So that's why now string builder with capacity wins. And string builder with capacity wins the whole way up everything. So you might look at this code and you'd say, right, okay, I'm going to go and set a capacity on all my string builders, right? This is for 1 to 10 strings. If we do 100 strings, we kind of get a different picture, right? There's clearly 3 good methods and 2 bad methods. And the good methods are twice as fast as the bad methods. If we add in 1,000, our good methods are now 4 times as fast as our bad methods. If we go to 10,000, you can barely see the good methods. So this is where knowing how much data you're processing is really important. If you're regularly concatenating 8,000 strings, then as long as you're not using one of these 2 methods, it probably doesn't matter. Now I say probably because sometimes it will, depends what you're doing, but there's clearly 3 good methods. So this is where I would say if you always only use a string builder and initialize its capacity, that's going too far, right? That's premature optimization. But if you put in the thought and the effort to decide, okay, I'm going to use one of these 3, but I'm going to pick the one that's easiest to debug or easier to read, then that's perfect, right? That's where I think you should get to. There's even an argument, if we go back to here, that if you're only concatenating, 7 or 8 strings, it maybe doesn't matter which method you use at all, depending on how often it runs. But you need to understand these things. This code, actually I've got on this slide. So yeah, so you need to know the context, right? You need to know how many strings you're concatenating, in this example, and how often you're doing it. And it's totally fine to just say, this is good enough, it's 4 times faster than what we used to have, but it's more readable than this one, which is 4.2 times faster. It's totally fine. Just make it a conscious decision. The thing you also have to consider is whether you're going after speed or memory, or both. And usually it's a trade-off, right? By caching things, we can make things faster, but they take more RAM. That's almost universal truth in programming. So you need to consider that as well. If we have 3 20-character strings, string builder is still twice as fast as concatenation, but it uses more memory. Now, 236 bytes is not a lot of memory, but maybe running on an IoT edge device it is. I don't know. If you're combining 3 2 meg strings, again, string builder is still twice as fast, but now it uses less memory, right? And so if you analyze if you have a benchmark that's looking at the wrong data, you'll get the wrong results. In the case where this pull request was, the data list was up to 3 strings, each one with about 15 characters. So actually, none of this stuff mattered. Data.aggregate was totally fine. And in fact, what we did was for readability, we actually changed it to use string concatenation because there was an series of if statements that would add things to a list and then combine them together. And we just said, well, let's just build up a string. And because where this code was used, it was like once on page load and then it was a single page application, so it never got run again. Didn't matter. But that was a deliberate decision, include a comment in the code saying, yes, I know we're not supposed to use string concatenation, but, and away we go. All right, some more examples for fun performance things. Dictionary versus IDictionary. So again, we have our benchmark, we have a memory diagnoser. We have 2 fields. One's a dictionary, one's an IDictionary, both string to string. And in global setup, we're creating one dictionary, and we're storing a reference to it in each field. One as a dictionary, one as an IDictionary. At no point are we adding anything to our dictionary. It's empty. And then all our benchmarks do is loop through an empty dictionary and return it because we don't want it to be thrown away. Does anyone want to guess what the graph's going to look like? I mean, it's kind of like, if it looked the same, I wouldn't be here, right? So this is what the graph looks like. This is kind of eye-opening to me. Using IDictionary is twice as slow as using a dictionary. And I mean, it allocates infinitely more RAM because dictionary allocates nothing, but it allocates RAM, a little bit of RAM. If there were things in this dictionary, the difference would actually grow. If you use an IDictionary, every call, every time you iterate through, it's a little bit slower. Does anyone know why? I heard it over there. Boxing. Someone said it. The answer is boxing. So a dictionary enumerator is a struct, which means it can live on the stack and it can be really efficient and it allocates no memory. But if you go through an interface, .NET doesn't know that it's a stack. You kind of lose that information. So everything has to be boxed to the heap. And then every call to any method on it has to be null checked. It has to be a virtual call in case there's inheritance at play. So all these things that structs can't do that .NET or the runtime can know about and optimize for, we kind of lose all that information. So this one's interesting because a lot of people have in their coding standards always code to interfaces. And there's lots of reasons why that's really good. But in the project I work on, the .NET project system, we've had multiple times where we've had performance traces that have pointed to this sort of thing, and we have deliberately changed from interfaces to concretes as parameters in certain cases to save hundreds of megabytes of RAM. So you kind of need to be open to any possibility, right? This is where I said question your assumptions. You assume that coding standards are good, and I mean, they are, but coding standards have a specific goal, and performance is not that. And hopefully maybe readability is, and maybe maintainability, but maybe not. You know, some coding standards are just about consistency because there's a high turnover of developers in the team. So you kind of need to be open to question things. If you're getting down to try to fix some code, you need to be open to all these things. Loops versus link. I kind of mentioned this one briefly at the start. So I'm old. I like loops. I like link as well, but when I start typing, my brain just writes loops by itself. So this benchmark, we have an array of 10 things, strings, and we're looping through, finding the one called 5, and returning it. It's a very simple filtering. And then with the link extension, the filtering being done in first or default versus filtering in where and then calling first or default. So not a huge difference here, right? And obviously the loop's going to win because again, it wouldn't be on the screen if it didn't. But the interesting thing here is the difference between the two link methods, I think. Plus, if you're going after memory, right, loops don't allocate. For loops don't allocate. It's as simple as that. They can be compiled straight to IL, has a bunch of go-to statements, and it's done. Link will always use more memory. I actually remember, I should have tried to find it for the slides, but I remember seeing a tweet by James Newton King, who wrote JSON.NET. And he said he commented out all the usings of system.link in his code, and then fixed up all the compile errors, and ran whatever tests or benchmarks he had. And it used 19 meg less RAM just by removing link, right? There is an overhead to it. Now, that's not to say it's bad and you shouldn't use it, but there's an overhead. The difference between first or default or where is interesting as well, and it comes from deferred execution. So essentially, the where method doesn't do anything. It just remembers that you want to filter when you get there. First or default is then the thing that does something. Of course, that remembering has to be stored somewhere. So minor differences like this can have an effect, and this, again, this is 12 bytes, right? We're not talking big numbers, but these are micro benchmarks, so you have to extrapolate these out. The other thing to consider when you're looking at link, particularly with benchmarking, is you've got to make sure you're measuring the right thing. So that was link over an array. That's linked to objects. If you're trying to work out whether to use where then first or default or just first or default, and you're using Entity Framework, then this benchmark doesn't tell you that answer. Because when you use Link to SQL or Entity Framework or any other link provider, it has completely different characteristics. I actually wrote a link provider once that did database access, kind of like Entity Framework, obviously not as big, but and in my provider, those two methods, the where then first to default or just first to default, they would have executed the exact same code path because that's just how I wrote the code. So you need to make sure you're testing the right thing. The other thing is, if you are using database, if you try and benchmark something without a real database, you're probably just going to get numbers that don't matter because the database access and the network and whatever is always going to be slower. All right, last one. Again, very simple. We have one string, and I'm calling to lower invariant, to upper, and to upper invariant. I did this one because I remembered seeing some guidelines in documentation that said, I think it was to lower invariant was specifically designed for performance, so you should always use that before you use a switch statement. And I thought that was interesting, so I thought I'd test it. So, now you may notice there's two graphs on this screen. So, the one on the left is .NET Framework, and the one on the right is .NET Core. So, in .NET Framework, to lower invariant is the fastest. The documentation is correct. Interestingly, in .NET Core, to upper invariant is the fastest. Now, clearly, there's not much in it, and it's probably not worth going and changing all of your code. But again, we have this situation where there's clear two worst performing ones and two good ones. And to lower is easy to read and it looks nice, but if you don't need culture, then invariant has a bunch of work it doesn't have to do. But the really interesting thing about this graph is the number in the top left. So .NET Core is twice as fast as .NET Framework for string comparisons. Not for everything, but for this specific thing, there's been multiple optimizations done. So even the slowest one in .NET Core is faster than the fastest one in .NET Framework. So when I said be open to anything, maybe you need to be open to changing a framework, right? If you're doing performance work on a .NET Framework app, especially with .NET Core 3 and WinForms and WPF being a possibility, it might be quicker to upgrade your app to .NET Core and don't even worry about the performance work because you might just get a free speed bump. Or certainly worry about it after you make that major change. But you also need to know the quirks of the environment, right? This comes down to testing the right thing. If you're writing your benchmarks in a .NET Framework console app and then you're deploying your code on a Linux box to .NET Core, you can't really make any decisions based on the number. So make sure you're testing the right thing. And then this is my ideal. This is my favorite code in .NET. This is straight from referencesource.microsoft.com. And it's a class called Hybrid Dictionary, which probably no one in this room has used because it's very old. It predates generics, and it doesn't really have a point anymore. But Hybrid Dictionary is a dictionary class, and its job is to it changes its internal storage depending on which one, or depending on what's going to perform faster. And if you told me, hey Dave, go and write a dictionary that changes its internal store based on what's going to perform faster, my mind would be racing with, right, well if we time every time we got an add method and we measure how long that takes, and then we maybe build up a table, or like, oh, maybe we could use machine learning, or we build a neural network in this, right? No, 9. 9 is the answer, right? Hybrid Dictionary uses a list internally. You add, and as soon as you get to 9, it swaps, copies your stuff to a dictionary, a hash table, and it uses that. That's all it does. So the reason I love this, because I think this kind of sums up the whole picture of what Donald Knuth was talking about, right? Here is a class where performance is super important, right? It's written on the tin. This is supposed to be the fastest thing. They haven't gone and written the most complicated, over-the-top thing in the world, because that would be premature. But they haven't ignored it. They have done exhaustive testing. They have, this comment is not me, right? This is in the code. They have carefully tested, and they have worked out that in most cases, and maybe being Microsoft and .NET, maybe they knew the real-world usage of this class from internal code, I don't know. But they have worked out that for most people, if we just cut over at 9, we get very good results We get a class that's easy to understand. It's probably got less bugs. This is the performance culture at work. This is what I love to see. I love to see comments as like, I know this looks weird, but. So in summary, should you always use a dictionary instead of an IDictionary? Personally, I think yes, but we can have that argument later. But no, like the answer to everything in programming, it depends. You have to do the thinking, and you have to not shy away from that thinking in order to work out what the answer is for every single case, because it always depends. So premature optimization isn't the root of all evil, but sometimes it is. And that's it. Thank you. Does anyone have any questions? If there's no questions, you can go get coffee early. Yeah? With, sorry? So the question was, did I test for aggregate with a string builder? I didn't. I suspect the answer will be somewhere in the middle, because the string builder will make those additions faster, but link's still going to have an overhead, and a lambda is still going to have an overhead. And in fact, if you want to know why lambda has an overhead, I'm talking tomorrow at 20 to 2 about what the compiler does to lambdas. But so I suspect that would be somewhere in the middle, but it would probably still be on the bad side in that it would probably still grow. Actually, no, maybe not, because the string builder will make it, yeah. So yeah, I suspect it'll be somewhere in the middle, but yeah, maybe it would be closer to the good results. As you grow your number of strings, it's probably going to hang down the bottom, not at the top. But the only way to tell is to measure. So that's right. Any other questions? Can't see. Yeah.
This might trigger some folks. Do you guys use any linting tools to highlight things that may require review?
That's a good question. So the question was, do we use any linting tools for things that may require review? There are heaps of Roslyn analyzers out there that can help with various situations. We specifically in the project system, and in a lot of code that's in Visual Studio, we use a series of analyzers for threading problems, because Visual Studio is highly sensitive to UI thread problems. That's kind of, I mean, it's not a niche, it's not specific to Visual Studio, but it is something that, you know, a lot of people wouldn't need. I know there are analyzers around warning you about hidden allocations for memory. They're really good. I've used them in the past. So things like if you have a method that has a param array on the end, if you don't pass anything for that params array, it'll warn you and say, this is still going to allocate an array even though you're not using it. And you could consider adding another overload if possible. So things like that, there's some good ones for. I don't recall any sort of general analysis ones, performance analyzers, but I'm sure there's some out there. I mean, there's packs you can get, like I think Code Rush and all those sort of things, and there's just hundreds of analyzers. So yeah, there's probably a lot. The trick with analyzers is if you have too many, your performance of your coding environment starts to, fail. So you've got to trade that off. Any other questions? Cool. Oh, yeah. So excuse me, the question was, sometimes in the results you see red highlights by benchmark.net, and it says things like 3 iterations excluded for some reason, and it's basically comes down to statistical analysis. There's a bunch of maths that benchmark.net does to work out standard deviations and that sort of thing. And so what that's doing is warning you that it's had to throw out some numbers, and therefore you kind of just need to take things with a grain of salt, right? Out of 100 iterations doing 2 million operations, if you'd had to throw out 3 or 4, maybe it's not worth worrying about, but maybe it is. If you get it repeatedly on like the same, running the same benchmark in the same environment over again, like on a computer that's plugged into electricity, then you maybe it means you're sort of benchmarking too much, or there's too much variance in there. And if you can narrow it down to focus on a different bit of it, or maybe this bit separately to this bit, you might get better results. But yeah, depending on how much it's having to exclude, you sometimes can ignore it. And that also depends on how close your results are, right? If you've got two things you're benchmarking and the numbers are really close together and it's had to exclude some, then you might not want to put too much faith in that. But if one's a clear winner and it's had to exclude some, maybe it doesn't matter. The other thing just on that to remember is that the numbers aren't important. Like, the numbers aren't real, right? That took 300 nanoseconds on my machine. Doesn't matter. It's not going to take 300 nanoseconds in production, especially not on a cloud environment where there's lots of web requests coming in or whatever. It's not the real numbers, it's the comparisons. And really that's so the cool thing about mentioning, I should have mentioned this earlier, so the granularity of stopwatch on my machine, the most granular thing you can use in .NET is 300 nanoseconds. On this machine, on this laptop, on battery power. I cannot time more than that if I just time it myself. So the fact that benchmark.net can even determine the difference is where its power comes in running that many operations and doing all that statistical analysis. So you need to kind of keep that in mind because, yeah, if something takes around 300 nanoseconds on this machine, I'm not going to notice it, right? Like, that's as fast as this processor can report things back to the software running on it, kind of thing. So, yeah, so don't get too caught up on the actual numbers. Cool. Well, thank you. I'll be around if anyone else wants to chat.